Okay, so here we're looking at energy distribution curves derived from spectra that I captured with my telescope, diffraction, grating, and camera for two particular stars, Betelgeuse and Bellatrix. So on the x-axis, you can see wavelengths of starlight ranging from 3,800 to 7,400 angstroms, and on the y-axis, you can see the amount of light energy emitted by each star for every one of those wavelengths that are listed along the x-axis. So the important point here is that the wavelength at which one sees the peak value of light emitted by the star is linearly and inversely related to the star's surface temperature. That's a principle known as Wien's law. So for example, in the first graph, you can note that the peak value of energy for Betelgeuse occurs at the light wavelength of 6,800 angstroms, which is quite large compared to the 3,800 angstroms wavelength at which the peak value of visible light from Bellatrix occurs. And since the wavelength at which the peak energy occurs is inversely related to the star's temperature, we've determined that Betelgeuse has a very cool surface temperature compared to Bellatrix, which makes sense because Betelgeuse is a red star and Bellatrix is a blue star. Now actually Bellatrix's peak energy occurs at 1,340 angstroms in the ultraviolet energy range, but my camera is sensitive only down to a minimum of 3,800 angstroms. I recorded the spectrum for these curves on March the 30th, and as I mentioned, I used a refractor telescope, a diffraction grating, and a color webcam.